Hi everyone, in today's class we're going to work through a few problems starting with the marble problem that we ended class with last time. Then we'll see two, maybe three, depending on how wordy I am, additional problems where we will apply the equations that we derived last time for projectile motion. I'll remind you, projectile motion is the motion that's occurring when we have an acceleration of gravity that's only acting downward. For instance, on Earth, we have acceleration of gravity only acting in the y direction. What we derived last time was the result that downward acceleration is only going to affect the motion in the y direction, and our velocities that could be in the x direction will not be affected. Only the velocities in the y direction will be affected. We will see with some additional problems today what that looks like. We derived these relationships. Let's move me here out of the way. Whoops, wrong window I'm moving. I don't want to move that one. Let's move this one. We derived these relationships last time. The x motion, the motion in the x direction, is motion with constant velocity. So I have only this relationship here. X is equal to x initial plus v in the x direction times t. Remember that our textbook uses typically v naught for v initial. So in our notes, I've been using v initial, vi. Our textbook uses v sub 0. So just be clear on the symbols that are being used here. In the y direction, we have accelerated motion. These are the same relationships that we had in chapter 2, except we've made the substitution, right, that the acceleration is negative g. So let's remind ourselves how we use these relationships. This diagram here is a diagram of the motion of an object that is just like the marble in the problem that we solved, that is being rolled off the table. It has therefore up here a sideways velocity here. So right here is our initial marble. We're going to follow the dotted line. There's also straight down. It's recreating that time-lapse photograph that we talked about last time. We have a sideways initial velocity. That initial velocity for the entire marble is only in the x direction. That's what we have all the way up here. Let me make sure that that's being shown on the, not quite. So let's go down like that. There we go. Our initial velocity of the marble is only in the x direction. As time goes on, each of those dots represents the marble an instant later, and an instant after that, and an instant after that, and so on. And we're seeing that the x velocity vector is not changing, because in the x direction, the only relationship we have is that the x velocity in the x direction final is equal to the velocity in the x direction initial, because ax is 0. And therefore, we can say that the location x final is x initial plus vx times t, because there is no change in vx. So I call it initial or final. It's just vx. That velocity being the same is shown in this diagram, right? Each arrow is the exact same length as it was before. Now, in the y direction, we have all of our equations for accelerated motion that describe what's happening there. We see that the y velocity starts out as 0. Initially, we were only moving horizontally. The y velocity starts out as 0 and gets bigger and bigger and bigger at each instant. Let's imagine that the floor is right here. This will save me from having to redraw the picture. If the floor is right there, nailed it. The question asked for the time it takes to strike the floor. It asked for this horizontal distance that the marble moves. Actually, I should probably, right, well, it only goes out to there. You know what I mean. The horizontal distance that the marble moves before it strikes the floor. And then I tasked you with determining that velocity of the marble. Here we can see that the velocity of the marble points down into the floor, right? It's moving sideways, but it also starts moving down faster and faster and faster. So we wanted to determine what this velocity is. Let's quickly work through this problem, especially the first few parts that we already solved, just again to get our feet back under us and to review a thing that perhaps you have a question or two about. So in this problem here is the problem that we started working last time. So we have, oops, I'm going to just pause just for a second. Okay, I wanted to resize my window. So the marble rolls along at a constant speed. We are told the distance above the table. So if we, and feel free to go back to your notes. I'm going to kind of go quickly through this. The things we were told and the choices we were making, we could say that y initial was 1 meter off the floor. Y final is equal to 0. We hit the floor. We don't know x final. We know x initial is 0 and x final is equal to something that we are looking for. Then if we think about the velocities, well, I'm going to move my list over here. The velocity in the x direction is 2 meters per second. There is no acceleration in the x direction, so as a reminder, I'll state that it's 0. In the y direction, we know that the initial velocity in the y direction is 0, right? Because we are moving horizontally at first. I'll make sure that I'm not covering up my writing going. Now our Vy final is something that we don't know. We're being asked for that in the last part. And we don't know t, right? T is another mystery. So if we look at the relationships that we have, let's start with, this is similar to what we did, whoops, wrong picture. Similar to what we did on Friday, right? It seems like a sensible place to start to say, well, I'm asked for, in part B, where it lands, x final. So let's look at this relationships. At this relationship for the motion in the x direction. Well, I don't have anything to go on here, do I? I don't have enough. I know 2 meters per second. I know I start at 0. But I need to find the time, and I don't have x final. Okay, so we've got to set this one aside. Instead, what we do is we switch to thinking about the motion in the y direction. We can independently use our equations thinking just about what's happening in the y direction. Even though the path is sideways, a little half of a parabola, I can completely isolate what's happening in the x direction and what's happening in the y direction with 2 different sets of equations. So in the y direction, we can look at this relationship, y final, equals y initial plus Vy initial times t plus 1/2 ay t squared. And we know the acceleration in the y direction because it's in free fall after it leaves the table. So putting in the values that I know, this middle term goes away, 0 times t. I can do that in my head. I don't mean to brag, but that's the only math I'm really comfortable doing. Anything that involves 0 in my head. Everything else I'm going to write it down or use a calculator. 1/2, and then the acceleration is negative 9.8 meters per second squared times t squared. This allowed us to solve for t, 0.452 seconds. Again, we did this at the end of class on Friday. Now that we have this t, now we can kick over to this side and say, hey, I can calculate x final. We started at 0. We have a speed of 2 meters per second, and I'm going to multiply it by 0.452 seconds. And that gave us x final as 0.904 meters. So that was part B, right? This was the answer to part A. This was the answer to part B. Now we can use the relationships that we have in the y direction to find the final y velocity. Remember, we wanted to find the speed. We want to know how big, when that marble comes right to the floor and it has that downward velocity like this, I want to know how big that velocity arrow is. That's what the speed is. We'll also do a quick calculation to determine the direction that it is under the ground. We did not ask for this on the Blackboard assignment, but we can find it now. I know that this velocity is made up of two components. One of the components is the x direction of the velocity, vx, and the other is the y direction of the velocity, vy, and I'm going to say vy final. Vx we already know. Vx is equal to 2. I can't stress enough that in the x direction, there is no acceleration. The velocity is constant in the x direction. In the y direction, we have acceleration, but since we found the time, now we can solve for the velocity that we get after allowing the velocity to change for that long under the acceleration of gravity, right? We know that the final speed is equal to the initial speed in the y direction, vfy, viy, plus acceleration in the y direction times t. One thing I'm going to point out, I just noticed I did it, I'm going to do it a lot. Here my subscripts are vyf, here my subscripts are vfy. I can never make a choice and keep it straight. They're not two different things. I'll try my best to keep them the same, but I'll point out right now that I don't always keep them the same. One's vy final, one's v final in the y direction. They're the same. I'm just being sloppy with my subscripts. So now we can calculate the final y velocity. We have 0 as our initial y velocity plus negative 9.8 meters per second squared multiplied by our time, 0.452 seconds. That gets us a final speed of minus 4.43 meters per second. That's VFY. Now I have both Vx and Vy for the final moment in time. I can calculate the magnitude of the velocity. This is the length of that arrow, right? It's going to be the square root of 2 squared plus 4.43 squared. I dropped the negative sign because I know I'm going to square it. Again, I'm just kind of going fast through this. That gives me a speed of 4.86 meters per second. And if I wanted to find this angle theta, remember here's Vy on this side, Vy final, or Vfy. I did it again. So I'm going to do an inverse tangent. I'm just doing some trig. Tangent minus 1 of Vy final over Vx. That's an inverse tangent of 4.43 over 2. If I put the negative sign here, it'll give me a negative angle on our calculator, so that's helpful. And I get negative 65.7 degrees. So that tells me the angle below that marble is, the velocity of that marble as it hits the floor on the way into the ground. So we see that in this relationship, or in this situation, I should say, again, that looks like this. We're seeing that as time goes on, the motion of that marble is such that the y velocity gets bigger and bigger and bigger, while the x velocity stays the same. We can use those equations to answer any question about that motion. Let's see another example of projectile motion and work another problem. The next problem we're going to work deals with Alan Shepard hitting a golf ball on the moon, which is a real thing that he did. This was Apollo 14. This was, so if you're familiar with Apollo 13, this would have been the mission after the Apollo 13 emergency, where they actually couldn't land on the moon and they had to come back, and it was very tense and they weren't sure they were going to survive. So the next time they do go up, Alan Shepard decides to play golf. These are the kind of, this is how you have to mentally where you need to be in order to be an astronaut, I suppose. Be like, well, we're fine. Now we're going to play golf. Anyway, he took a head of a golf club. It was a 6-iron, and he affixed it to some long rod that they had for some kind of tool. And he is said to say that the ball went for miles and miles, and it did. hang in the air for many more seconds because of the moon's reduced gravity. If we assume that he actually had a regular tee shot speed, which he didn't, he was swinging very slowly, he's got his big spacesuit on. I read an article, I think it only went 50 yards or something like that. But if a regular golfer had a club speed of 64 meters per second, but now with an initial launch angle of 30 degrees, this is where things are going to get interesting. Let's see how far that shot would go. I'm going to show a picture of what this trajectory looks like. If we go back to this here, let's go down and down. These are the problems we were just making. There we go. This is what that golf shot is going to look like. It has the angle's much smaller, but we see that our initial velocity here, let's get a different color other than green, has both X and Y components. We are launching it up at an angle. The Y velocity will change as time goes on because of the vertical acceleration. We see in this diagram, again, the X velocity does not. So the motion in the X direction is quite simple. The acceleration in the Y direction is what's going to determine the time that this projectile is in the air. Using what we're told in the problem, same formulas we've already had, but a new situation. So let's work it and see what we get. So if we go back to, here we go. Let's jot down what we're told before we go onto a new page to work this problem. We are told that the velocity is 64 meters per second at 30 degrees above the horizontal. We are told that the acceleration is not minus g because we're on the moon. It is negative, and it just has a different value, 1.6 meters per second squared instead of 9.8 meters per second squared. And we want to know how long it's in the air, and how far. So what we don't know is t, and we don't know delta x. So it doesn't seem like we're given an awful lot of information. However, that velocity that we're given is actually 2 bits of information because we are told the entire vector, which means we can decompose that vector into components. We'll draw a picture to show what we mean. Our velocity is up at an angle like this. So it's a 64 meters per second velocity at 30 degrees. We can break this into components, Vx initial and Vy initial. Using the same trig functions that we had in our previous classes, we have the magnitude, so the x component would be the magnitude of the vector, 64 meters per second, times cosine of 30 degrees, and the y component would be 64 meters per second times the sine of 30 degrees. So this gives us our x and y velocities. We have the x velocity being, I have it down here, I didn't calculate it out. The y velocity is 64 times sine of 30, which is 32. And let me pause and find a calculator. In the x direction, that velocity is 55.4 meters per second. So the questions we were asked is how long does it take and how far does it go? Well, let's think about that time first. We know that we have the following relationship in the y direction. Y final is equal to y initial plus Vy initial times t plus 1/2 Ay t squared. This, as opposed to the marble problem, this problem involves a golf ball starting on the ground, going up into the air, and ending on the ground. The total flight is from ground to ground. If we draw a tiny little diagram here, right? We start here and we go up and then we come back down. And that's y equals 0. So I've got 0 and 0 here. This is actually pretty straightforward. Plus, I've got 32 meters per second as my initial y times t. Plus 1/2, the acceleration was minus 1.6 meters per second squared times t squared. I can solve this. This one actually ends up being pretty simple because I've got the zeros. I don't need the quadratic. I can simplify this. I'll let you do that on your own. In the interest of time, we'll say, okay, this is going to be a 40-second time interval. Anyone who's played golf knows that that's a pretty long time in the air for a golf ball. But we're on the moon. The reduced gravity is what makes this go so far. Now with this time, what do? In these problems, almost always, unless we're given different information, so I shouldn't say almost always, very often is what determines the time. The acceleration in the y direction is what's going to govern how the velocity behaves when I hit that turnaround point, when I start heading towards the ground, etc. Then we'll use that time in the x direction equation to determine how long it is. I realize the next problem we're going to do, we're going to be told how long it is, so we're going to work backwards, but we'll see how that goes. So if I use that time in the x direction, I know that x final equals x initial plus vx times our time. Well, we started at 0. We have our x velocity of 55.4 meters per second. Let's put units on that so we're clear of what's what. Meters per second. And then a time of 40 seconds gives me a final position of 2,217 meters. A mile is 1,600 meters, so it is more than a mile. Now, again, in real life, he didn't hit it this far because he couldn't swing the club that fast because he's in his moon suit and it's not an actual golf club. If a real golfer or an average golfer hit the ball as fast as they normally do with the moon's limited gravity, it would go this far. What you might have noticed if we've taken a physics course before, especially something like physics in high school, from my experience, it seems to be often taught that we have to hyper-focus on this point up here at the apex of the trajectory. It is true that at this point, the velocity in the y direction at this point is 0 meters per second at the very top. It is true that for this trajectory, this path, when I start at the ground and end at the ground, there is a symmetry about that top point. So I could find the time it takes to get to the top and then double it, and that would be my time. You can go ahead and do that calculation. You'll see that if you use a different equation where we put y final is 0 and the acceleration of negative 1.6, you can calculate that the time it takes to get to the top is 20 seconds. I didn't do that because not all of our problems are going to have this symmetry. It's great to have this intuition that, okay, at the top, I do know that Vy is 0. Depending on the question, we might need that. Often we don't. So don't fall into the habit of, I have to find the time to the top. I have to know where the top is, how far it goes. I wasn't asked how tall the trajectory was. I wasn't asked what the maximum height was, so I don't care. Think carefully about the question you're being asked. Often, we only need one of our formulas to answer it, and we're off to the races. Let's work a problem where that symmetry is not apparent, or is not in the problem, I should say. So we certainly can't use any of our techniques to, well, what's the time to the top and let's double it. If I have starting and ending heights that are not the same, I cannot utilize any of that symmetry where the time to the top is half the time of the total flight. So here's the next problem we're going to solve. We have a quarterback standing on the 35-yard line, throwing a football directly downfield, releasing the ball out at a height of 2 meters, which if you are average height is a little bit above your head. So that's good, reasonable and realistic. We are told the initial velocity, 20 meters per second, directed 30 degrees above the horizontal. So just like the previous problem, we are told where what the velocity is and where it's pointing. The quarterback throws the ball too hard, so the pass goes over the head of the intended receiver. The receiver is right at the goal line. So we are told in the context of this problem where the X location, the final X location of interest is. We want to know the height above the ground as it crossed the goal line where that receiver was. And then I give a little note of conversion that 35 yards is roughly 32 meters. Let's draw a cartoon. Let's draw a little cartoon of what's going on in this problem. So we have our quarterback. I want to be sure that I've got this problem pulled up here. So we've got, here's the football field. Here's a perfectly drawn quarterback. They've got a little face shield and they've got a helmet. I don't know. It's a big helmet. Anyway, it's late. And here's the football, okay? We are told the initial velocity of the football, and we know that the football is going to have a trajectory that maybe is something like this. And here we have our receiver. And we know that the height initial, so y initial, is 2 meters off the ground. We don't know what y final is. We are assuming that it's higher than what the receiver can reach because we are told in the problem that the receiver cannot catch the football. Furthermore, we are told that this distance here, so if x initial is 0, x final was 35 yards, which is about 32 meters. So looking at that dotted line trajectory, we see that the starting and ending at the same height, like the previous problem with the golf ball, is not true in this problem. We're starting at 2 and we're ending somewhere else. I don't know what my final height is. So if I were to make in the y direction the values that I know, y initial is 2 meters, y final is, that's what we're asking for. I do know my acceleration. We're back on Earth, so we have negative 9.8 meters per second squared. And I do know my initial y velocity. Vy initial is going to be 30, I just had it, 20 meters per second times sine of 30. So that's 20 meters per second sine of 30. Why did I do that? Well, remember, our football is launching up. That's not a 30-degree angle, Jeffrey. Shame on you. Here we go. That's a bit more like it. That's the direction that our football is being thrown, 30 degrees above the axis with V initial equal to 20 meters per second. That means that it has X and Y components. So pardon me, a little bit of a slippery stylus. Now it's wiggly, but I don't care anymore. Vx initial and Vy initial. So Vy is 20 times sine of 30. That's just how much of the initial velocity is in the y direction. I don't know what Vy final is. In this problem, I don't think I'm going to care about that. So what are we going to do to find the final height? Well, our equation that uses the final height is the following. We have that the y final equals y initial plus Vy initial times t. We're starting to see that we've got an issue. 1/2 a t squared. I have a. A in the y direction. I have my initial height, 2 meters. I have my initial velocity, 20 times the sine of 30, which ends up being, I don't know what it is, 10 meters per second. I don't have t, and I'm looking for y final. We might kick out to the other relationship that says v, just for a moment, vfy squared equals viy squared. Again, I've switched my subscripts, forgive me. Plus 2 times the acceleration in the y direction times delta y final minus y initial, but I don't know vfy. I cannot say that it's equal to what we started with because it is not a symmetric problem. I don't know what it is. I'd have to solve for that. And the only other relationship that allows me to solve for v final in the y direction involves time. So right now I'm stuck. But wait, we haven't thought about the x direction yet. In the x direction, I'm going to switch colors because I'm talking about x. We know that, let's go up just a little bit. There's our picture again. We know our final distance, our final position rather, and our initial position. And I know the x velocity because there is no acceleration in the x direction. So I can say in the x direction, x final equals x initial plus vx times t. Our x final is 32 meters. Our x initial, we'll say we start at 0. And now we've got vx, which is the x component of our initial velocity. So for that, I'm going to say 20 meters per second times cosine of 30 degrees, all that times t, right? That whole thing in big parentheses is vx. This allows me the time to find the time that the ball is in the air. I'll take 32 and divide it by 20 times cosine of 30. That is a time of 1.85 seconds. That's the time that the ball is in the air. Now I can use this in this relationship here to find yf. Let's do that on a clean page. So now that I have the final time, that's our next problem. We'll probably end up doing that on Monday. Y final is equal to y initial plus vy initial times t plus 1/2 ayt squared. I'm looking for y final, so that can stay right there. We started at 2 meters off the ground. That was our initial position. Again, sometimes these problems are taught in a way where wherever you start is 0, and then we're finding the height change from 0. That's fine, but it's usually a bit more straightforward to always call 0 the ground, except in a few circumstances. So all we have to do is we have to just put in 2 instead of putting in 0. Put in 2. It's just a little bit more algebra. You're not going to be that much tougher off. Plus vy initial, which was 10 meters per second, right? Yep, I'm remembering that, right? Remember this we got from doing 20 meters per second times sine of 30 times the time that we just calculated, 1.85 seconds, plus 1/2. Don't forget that we've got negative 9.8 meters per second squared. Just a word, well, let's finish this up and then I'll talk a little bit about sines again as a reminder. Just a quick word about sines, right? If this is positive because it was going up at an angle, this has to be negative. We have to be sure that our sines are always telling the same story. So we calculate, cruncha, and you get a final y position of 3.73 meters, which is pretty tall. Most professional football players, receivers, probably could jump that high and get it, so it's probably their fault. I'm a Packer fan, so everything is the receiver's fault. Aaron Rodgers makes no mistakes. So this is obviously what happened in this problem. The ball sailed over their head, or they didn't turn around, or they weren't ready for it, whatever the case might be. key here in this problem is identifying what information we have and making sure that it goes in the right spot in the equations. It doesn't get any more straightforward than that. We don't have any new equations. All of our equations, I'm purposefully starting at the exact same point, and we're practicing on putting the stuff in the right locations. Very, very, very important as well is remembering, please, 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 in the x direction, I beg you, we only have this relationship. We have constant velocity, zero acceleration in the x direction. In the y direction, these problems, I realize the problems that I've picked, we've only really used these. We haven't asked about the velocity. We could, a different problem could want to know what the velocity is at a certain time. So another equation that, again, we haven't used in these problems, but is just as valid. Oh, I had to pause. I thought I was going to crash. That we haven't used, but it's just as valid as Vy final equals Vy initial plus Ay times t, or minus gt, if we say that Ay is minus g. We just didn't happen to use that in these problems, but these are the two relationships that we most commonly use. There's that third one as well that just takes out the factor of time. And that's all dependent on what we're being asked for. We had questions about positions and times, so we use the relationships with positions and times. The point I'm getting at is in the y direction, I have acceleration, so I use these equations for accelerated motion. In the x direction, I have zero acceleration. Ax is equals 0 in free fall. So I only have the constant velocity equation. So instead of squeezing in the last problem, I'll ask a second question on this football player problem, and then I'll leave the calculations up to you to answer it for your in-class work for the day to be sure that you're keeping up with the lecture. So I've talked about the equations that we haven't used, and it just struck me, well, why don't I ask a question where we can use those equations? So let's say for the same scenario that we just talked about, that's summarized in the problem statement here. So for what we were just solving for, all the same information, which means that our time of 1.85 seconds and our height is 3.73 meters. Let's say that we have a receiver with enough of a vertical, which is probably, again, pretty easy to imagine. They can jump pretty high. Although, I don't know, almost 4 meters. That's pretty tall. Let's just say that we've got this superhuman receiver. And they do jump up and catch the ball. I want to know what the final velocity of the ball is. So I'm going to ask on Blackboard 3 questions. I want to know the x component of the final velocity. I want to know the y component of the final velocity. And I want to know the speed of the ball when it hits their hand. So you're going to resolve those as a vector. So we did find, to recap, we found that y final is 3.73 meters, and the time that it took is 1.85 meters, and the other information is given in the problem. I want to know what is the x component of the final velocity. I want to know what the y component of the final velocity is. And I want to know what the magnitude of the velocity is, right? The speed. So I want to say, we can imagine that, okay, let's say someone is able to catch the ball. What are they going to be experiencing when that ball hits their hands? So practice using some of the other relationships that we didn't use. Think carefully about what I've been saying about acceleration so that you can think about what you need to calculate and what we already know. And these 3 answers will be what you put in on the quick little assignment on Blackboard, just to, again, show me that you're keeping up with things and watching these Friday lectures. On Monday, we will be meeting in person. I'll probably send out a reminder email over the weekend to that effect. I thank you for your attention all these virtual days, and I can't wait to see you in class in person to finish up the material for this week to get ready for our first test a week from today, if you're watching this on Friday. Good work. Let me know when you have any questions. You guys are doing great. Keep it up. I really appreciate your hard work.